Hi, it's Mr. Anderson, and in this video I'm going to talk about water, a polar molecule. What does it mean to be polar? It means that you have a charge. The electrons are shared unequally, and as a result of that, water has these amazing behaviors that allow us to survive on our planet. And so let's start by looking at one water molecule. It's made up of one oxygen atom and two hydrogen atoms, and what you should know is that oxygen is highly electronegative. What does that mean? It's going to pull electrons towards it. And if we were to look at those levels here on the periodic table, aside from fluorine, it's going to be the highest one there. And so why is that? Well, if we go across on the periodic table, we're seeing an increase in electronegativity. Why is that? We're increasing the number of protons in the nucleus. Therefore, there's more positive charge on the inside, so it's pulling those electrons towards it. And you might think, well, then as we go down on the periodic table, why doesn't it increase there? Well, as we go down, we're filling in more levels of electrons. And so these electron levels that are filled are shielding that pull of the protons on the inside. And therefore, we have to go up on a periodic table to get electronegativity increases. And so oxygen's really high. It's pulling the electrons of hydrogen closer to it. And so what you get is a partial positive and a partial negative charge. In other words, the oxygen's always going to be negative, and then the hydrogen's always going to be positive. And so you can think of it almost like a magnet. There are going to be poles or two sides to it. And just like magnetic fields move out around the magnet, you can imagine these imaginary fields around the water molecule as well. And so on the top, where the hydrogen is, we're going to have positive charges, and then on the bottom, we're going to have negative charges. And so imagine trying to put a bunch of magnets together like this and just holding them there. Now you know that those similar poles are going to repel each other, and so if you were eventually to let go, it would quickly shift to a shape like this, where south meets north and north meets south. The same thing would occur with water. If we put water molecules like this, all of these negative charges of the oxygen molecules are going to repel each other, so it'll quickly orient itself like this. And so water will always be oriented so the positive of the hydrogen and the negative of the oxygen are attracted to each other. And so what do we call that attraction between these? We call those simple hydrogen bonds. And so the hydrogen bond would be represented with these dotted lines. It's an attraction between the positive hydrogen and the negative oxygen. Sometimes we'll see hydrogen bonding with nitrogen as well. Now, what are some of the properties that we get as a result of this polarity? The biggest one that you can see right away is cohesion. What does that mean? If you think of this as one water molecule and this as another water molecule, then the positive here is attracted to the negative here. So if I pull this in this direction, this is going to go with it. And so it's holding all of those water molecules together. And so the surface tension in this water right here is caused by all the hydrogen bonds in the water molecules. Where this doesn't occur on our planet, but in space or in orbit around our planet, this is a big globule of water, and it's just floating there. What's holding it together is going to be the cohesion or the hydrogen bonds of those water molecules. What's another property? We have capillary action. What does capillary action mean? Well, if we were to look in this tube, it's just sitting in water, there's starting to be adhesion to the sides of the tube. Now, how is adhesion different from cohesion? Adhesion is when water is sticking to another surface, anything that has a charge. And so you can see it's kind of creeping up on the side. What's pulling the other water molecules along with it? That's going to be cohesion. But you can see as we decrease the size of that tube, it goes higher. And as we make it smaller, it goes higher yet. And in fact, if we make it microscopically small, so like the xylem, which are these tiny tubes in a tree, that's how water is moving all the way up a tree. There's evaporation of water up at the top, and then there's this connection of water all the way up these tubes to the surface. And so it's moving all that water through a tree. What's pulling it up? It's going to be the driving of that energy from the sun, but it's the connection of all those water molecules. It also accounts for the high specific heat of water. What does that mean? It's really hard to change the temperature of water. And the reason why is to change the temperature, you have to pull those molecules apart. And if you want to evaporate it, you really have to free up one of those water molecules. And so I live in Bozeman, and so Bozeman looks just like this, surrounded by beautiful mountains, but we're at about the same latitude as Seattle. Now, Seattle, instead of being surrounded by mountains, is surrounded by water. And since that water has this high specific heat, what it does is it moderates their temperature. And so this is the average high temperature in Bozeman and in Seattle. And you can see Bozeman is this yellow line. In January, it's going to be in the 30s or high 30s. And then in the summer, it's going to be in the upper 80s, pushing 90. But if we were to look at Seattle, its temperature is really not going to vary that much. And it's rare that they have really icy roads and a lot of snow. And it's also rare that they're going to have 100-degree temperatures in the summer. Why is that? It's the high specific heat of the water that's surrounding Seattle. So for example, in the summer when it gets really hot outside, a lot of that energy is going into the water itself. It's absorbing a lot of that energy. And as it does that, it's kind of moderating the temperature. It's a good reason why you're filled with water as well. If you weren't, our temperature would change radically over the course of even a day. Another property is that ice floats. And you might think, well, that's obvious. But with most matter, with most molecules, when you cool them down, they become more dense and they would therefore sink. But water doesn't do that, and that has to do with these hydrogen bonds in here as well. So as it cools down, it's forming this beautiful three-dimensional matrix, which allows it to actually decrease density. Why is that important? Well, if it didn't do that, then ice would settle at the bottom of the oceans, and we would quickly be a frozen planet. Another important thing about water being polar is that it's a good solvent. And so this is a PHET simulation. What I'm doing is adding a little bit of sodium chloride or salt to water. And you'll notice what happens, that when we add that to water, it breaks apart into its ions. And so the sodium and chloride ions are actually being ushered away by the water molecules. So if we get rid of the water, it goes right back to that ionic salt. So if we zoom in a little bit closer, what's going on? Well, let me kind of pause it right here. So what do we have? We have this chloride ion, which is going to have a negative charge, and it's going to be surrounded by the positive parts of the hydrogen. Likewise, we have this sodium ion, and so it's a positive charge. You can see that it's being surrounded by the negative charges of the oxygen molecules. And so as a result, that allows us to dissolve material really, really quickly. And as we move materials around in our body, it's important that we're made of water, a very good solvent. And there's this saying that like dissolves like. And so let's say we have water, and then we throw a little sugar, a disaccharide next to that. Well, what do you see? A bunch of oxygen, a bunch of hydrogen, and so that's going to be polar as well. And so we're going to have areas that are negative, and so the positive hydrogen is going to connect to that, and areas that are positive, and then the negative oxygen is going to bond to that. And so what happens when we add sugar to water? It's going to dissolve quickly. And the reason why is that like is dissolving like. Now, if we were to look at another molecule, this is a triglyceride or a fat. Doesn't have a lot of oxygen and hydrogen together. It's mostly made up of carbon and hydrogen, and those are sharing electrons equally. And so it's hard to dissolve something like that. And so what happens when you pour, for example, oil into water? It'll settle out. And so anything that has a charge, water is able to break down. The only exception would be things that are non-polar. So water is an amazing molecule. It allows life to exist on our planet. And if it wasn't polar in nature, life probably wouldn't exist. And as we start to look for life out in the universe, what are we generally looking for? Water. And so where's a great place to look? Europa is one of the moons of Jupiter, and we think that there is a liquid water ocean underneath an ice surface. And so if we could eventually get there, we might find life there. And so that's water. It's polar. It's amazing, and I hope that was helpful.